transnational access?
We have on the clinical side, yes, we have some hours left. I guess Angelica has the data on GSI research beam time.
Yes, so we have finished the CNAO and the HITRIplus ones for the research, but we still have some hours for going to GSI to make research with their beams. And then we have some clinical access availability still there.
Perhaps you can say something.
Now, someone else.
Yeah, clinical access means that maybe for the people that is newcomer to these meetings or in general to HITRIplus, is the possibility to visit the facilities, the 4 facilities delivering carbon ions for treatments in Europe for, let's say, get trained, get informed on the clinical activities, which kind of tumors, comparing things. So the issue is clinical research, of course, but is the occasion to compare modalities to understand for which patients, in particular, hadron therapy with carbon ions is, let's say, interesting and used. So please, if you have clinicians interested, get in touch with me or directly with Angelica, and we can forward to the committee that is judging the request for this kind of access to. This is fully reimbursed. Is also covering the cost of travel, staying. We have a format of 2-3 days in the facilities where there is the possibility to see all the steps that bring the patient to the treatment, and it's, I would say, interesting for clinicians, medical physicists. Alejandro, if you are interested, you are a referee, so I believe you cannot apply for the moment.
Well,
in the future.
Well,
yeah, just in the next months. Just wait months.
Well, he can't, but his team could. Okay, so maybe we should start thinking about, shall we? No, 1 more minute. Okay, so I'm actually going to start now. The academic 5 minutes are over. Good morning, good afternoon, good evening, depending on where you are all sitting right now. It's always a pleasure to welcome you all to the seminars, the monthly seminars we organize under HITRIplus. And just as a reminder, because I've had a few requests when people say, well, I have something else, can you record it? All the seminars are recorded and they are appearing on the HITRIplus YouTube channel. So absolutely they are open and they are there, because one of the reasons for doing the HITRIplus seminars is to share knowledge and make sure that people are aware what's going on in the field. And at this point, before I introduce Pavel, of course, that means if anybody's interested in giving one of the seminars in the coming months, please let us know, okay? So now I want to welcome Pavel Moscow, and and I want to say that the first time I heard about this PET with plastic scintillators was exactly 10 years ago in our ICTR PhD conference in Geneva. And one of the reasons I say this is because, you know, it takes time for translating to the basic idea to an application. And you never know what the steps are. So anyway, it's a great pleasure, Pavel, for us to be, to hear about the steps, where you are, what's happened, where the future is. But just to say, he's professor of physics and the head of the department in Krakow and the Jagiellonian University, which is a beautiful place. The first time I went there, I was thinking, wow, I should come back here. Anyway, so he's leading the JPET collaboration, has won many awards and prizes, as well as teaching, which is also very important. So Pavel, The floor is yours. Please do tell us prospects of proton beam range monitoring and hypoxia with your JPET.
Maciej, thank you so much for this kind introduction. I will try to share the screen first. Oops, not this.
It's not full screen yet. Ah, there we are. Perfect. Great. Thank you.
So I would like to present you what we are doing here in Krakow. I saw that some of the members are also connected and some experts from various fields. So I hope I will not talk too simple things, but I would like to present you the prospects of proton beam range monitoring and also hypoxia assessment. The first one, I personally think, is quite close to possible application. The second would require still a lot of research, so I will show you some rather the early stage research and idea. And all this with the modular JPET. Here I have some disclaimers, which are the patent applications. This is the city Manjit was talking about, so please come to visit us next time for some conferences or seminar. And I will talk, the first part, 2 parts of my talk will be devoted to explaining you how we are developing the electron emission tomography scanner from plastic scintillators, and then how with that scanners we develop the imaging of positronium properties in a body. And the second part is connected to that possible hypoxia assessment during the proton beam range monitoring. And then after that introduction, I will show you at which stage we are now as regards the applications of that tomography system from plastic scintillators to proton beam range monitoring. And by now we've published 2 articles which are showing the feasibility study, the simulation study, and we did an experiment which are not yet published, but I will show you some preliminary results. Experiments with monitoring the beam impinging on photons. So that JPET comes from Jagiellonian PET. Jagiellonian is the name of our university. This is the oldest building we possess, Collegium Maius, and I can't resist from starting to telling who was by now our best student. He was studying astronomy and as those days. And now we are a group. I still have an old photo. Not all members are here. So we are now a faculty of physics astronomy, so some connections to this gentleman before is still there. And this is part of the group which is belongs to the nuclear physics. And we are doing development of all these technologies, positron emission tomography and reconstructions. And by now we also came to the era of clinical studies. And so we joined the group of medical physics under the guidance of Professor Stempin. So we are now a collaboration of physicists and medical physicists, also medical doctors, IT programmers, so quite interdisciplinary. I know that all of you are well acquainted with the positron emission tomography, but anyhow, for the completeness, I will start from explaining some things. And the main reason is that I would like to tell you something which is not that known, which is regarding the beginning of the isotopes which are now used for the positron emission tomography. And the most used isotope for labeling ligands is fluorine 18. And this fluorine now, this is inside the body, emits positrons, which annihilate with electrons. And I am pointing that because this fluorine, the radioactive fluorine, was discovered by in Poland by the Ludwig Wertenstein. He was a professor at in Warsaw. They were bombarding nitrogen with alpha particles and observed that when taking out the source, there's still something which irradiates, and proven that this is fluorine, and published an article in Nature. You see here, this is an interesting story in Nature in 1933 in the volume 133, and I am telling you that by purpose, because at the same year, I don't know when you see my at the same year, at the same volume, only the page is different. Irene and Frédéric Joliot has published that alpha particles irradiating on boron are leading to the production of artificial radioactivity, and they got a Nobel Prize for this discovery. And about this gentleman, I am pretty sure that maybe even all of you hear the first time. The difference is the page number at the Nature. So that's a story about this fluorine. Now coming back to that plastic scintillator. So the main motivation for that was to make the tomography system cost-effective, but then came other advantages. Nowadays, all the tomography systems are using crystal detectors, LISO, some older BGO, for detecting annihilation photons. And the reason to try to develop a method which will be cost-effective is just when looking at the map of what is the amount of PET systems in various countries in the world, one can see that maybe even the statement is close to true that almost nobody in the world has access to that technology. So most of the country has nothing, 0, or something between 0 and 1, closer to 0. Poland, when I am from, has now still not 1, is between 0 and 1, close to 1 per million citizens. There are only a few countries like US, Japan, which have it at the level which is maybe can be called saturated, but still not used, not at the level that it can be used for screening. So the reason to start that research was to find out the way the cost-effective tomography. And now you see our latest solution is, this is an animation of the technical drawing. It's like modular, and we can reconfigure there, and this is also light. So these are the present advantages of the technology. We use plastic scintillators. So here you see an example of annihilation point, two gamma quanta interacting in the scintillator, and we measure the position in the detector along that scintillator from the time when the scintillation photons arrive to that edge and arrive to that edge. So this can be made long, and this is the one of, there are of course many disadvantages. I will tell two major, but this, that we can use a long strip of a plastic scintillator, is an advantage. And this comes from the fact that if you now compare, this table is busy, but maybe I can just point the main features. These are plastic scintillators, and the 3 lines above are crystal scintillators. So if you look at here, at the attenuation of light photons in crystals, it is about 5 to even more than 10 times stronger than in plastic scintillators. And some of them may even have a mean path of the optical photons up to few meters. So this makes it possible to make plastic in a long strips and still have quite a lot of light at the edges to see a signal. Disadvantage is that the density is low. It's 7 times lower, which means that the probability to interact is much lower. But another advantage is that the signal duration is much shorter, which in principle makes them more suitable for good timing. So all the photons are emitted here with the K time in the order of 2 nanoseconds, and in crystals, it's like 20 to even 100 times longer times. So we can make it long here, and so they can work, as you see here, as light guides, as scintillators. And plastic scintillators are very robust. So this is like plexi. One can produce them in various shapes relatively easily and cheap. They are like about 50 to 80 times cheaper than crystals, depending on which crystals one compares to. The lower efficiency in that solution which I presented can be compensated by making few layers. So in the standard solution, you cannot use more than 1 layer because anyhow everything is absorbed in the first layer, and the detectors are here on the surface. But we may use detectors at the edge. We can make more layers, and making large solid angles and more layers, we can compensate for the low efficiency. And the cost effectiveness comes from 2 reasons. One is that scintillators are, as I told, 50 to 80 times cheaper than crystals. And the other reason is that the detectors are at the edge here. And in the standard PET systems, the detectors are covering the surface. So we have less electronic channels and cheaper material here. Altogether, the estimations are that building like a PET for a whole body, large PET, one can make it even 10 times cheaper. 5 to 10 times cheaper, depending on how many rings and what solution one chooses. So in order to make such tomography possible, we had to develop a lot of various methods, starting from the signal processing. So we sampled the signals. These are very fast signals, like 2-3 nanoseconds broad. So to sample them, we developed a method with FPGA systems. I will not go to the details of that, although I can discuss if somebody would like to. I just mentioned that it was a lot of development. We have documented that in many articles by now, but I will just show you in figures the history of that development. So Majid was talking about 2014, when we came from the stage of 2 strip scintillators to the first prototype of 24 scintillators. Then we built a prototype which is full scale, and we use it still in the laboratory, which was for ex vivo and laboratory studies, and it is still for the studies. Then we built the tomography system, which I have shown you, with which we do the clinical studies in the hospital because it's portable. And also we did an experiment in the Hadron Therapy Center, which I will show you. And now we are building a total body PET. This is still rather older transparency. I think the realistic time to make it ready is 2028. We got this end of last year, which means in practice this year, we secured funding for building the total body PET for 2.5 meters from plastic scintillators. So this will be a a tomography system for dynamic studies. So I will now show you some examples from that laboratory system. So this is how it looks like. Here you see a plastic scintillator, steam vacuum tube photomultipliers. This is to compare with the real human beings, the colleagues who contributed to building the detector. These are 3 layers, and the difference to the standard tomography systems, but not that much to the physics detectors, is that we can detect not only annihilations to 2 photons, but also to 3 photons and also multi-photon events, because the data acquisition is working in the so-called triggerless, or sometimes mentioned as single mode acquisition, which means we register everything, which also means that we store a lot of noise. But for the research phase, it's very practical because we can study very many phenomena not restricted to any specific decay or reactions. So these were our first studies. You may see it as a human being, a phantom with a cylinder with the porous material. So this was also for physics studies. We developed with collaboration with the Lublin University colleagues, Professor Jasińska, such a material which allowed us to cover the cylinder. And this material has pores in the size of few nanometers. So the lifetime of positronium atoms is long in that material, and it keeps on the surface. This is a sodium source emitting positron. They are annihilating here, and this was our first image, just calculating the time difference between the annihilation, between the points when the photons were registered. So we have position and time, and we can reconstruct. This is not a mathematical reconstruction. This is just iterative reconstruction. This is just a points density of annihilation point. If we do a maximum likelihood estimation, maximization, reconstruction, then we can see much better images, but this is just to show you that it works. So this was a part about the basics of this plastic PET. Now I will come to the second part, which we call positronium imaging, which is the method for imaging, not only making spectroscopy, but the clue in that is to image the properties of positronium's atoms, and the aim is in a body. So here you see again the same example when positron from fluorine is annihilating. But if you would closer, I know that all the audience are some experts from positron, so you have to forgive me that simplifications, but I saw also that maybe some of you are not so familiar, so I make it simple. So this positron and electron may form a positronium atom, and in the material like our body, tissue, water molecules in the cells, this happens in about 30–40% of cases. And again, this is simplified how it may happen that this positronium is formed in a body. This is a molecule of hemoglobin. This is an example when the positron at the end of the text, when it is having energy in the order of tens of electron volts, ionizations happens often, and at the end there is a lot of free electrons, and positron may form an atom, may form a bound state or quasi-bound states with one of these free electrons, and if there is a free space between atoms, it may live there for some time. So this is how it may be, and it also happens in our body. And there are 2 ground states of positronium atom. One is when the spin is 0. This is then parapositronium. And symmetries of these atoms, like charge conjugation, parity, force it to decay into 2 or even number of photons. I would be pleased to explain it, but if somebody asks afterwards. The other state is spin 1. It has different symmetry, so it cannot decay to 2 photons. It may decay to 3 with lower probability to 5 and so on. Therefore, the lifetime of that is much longer because there is more complicated decay, there is more Capri constants and smaller phase space. Lifetime of that is like 1,000 times, more than 1,000 times higher than that one. So in vacuum it is 140 nanosecond. So the changes of the lifetime in the matter may be significant, and this is what I think may be useful at some day for also for the medical purposes. Here is an example. What are the 2 crucial processes in our body or in the molecules which may shorten the lifetime of that positronium, which is decaying to 3 if it does not interact with the surrounding atoms, but it may interact also when exchanging the spin or interacting with the paramagnetic oxygen, and oxygen we use for the metabolism. So this is the process which is shortening the lifetime, one of the processes, because then due to the this is called conversion from spin 1 to spin 0, ortho becomes para and decay quickly. So this is shortening the lifetime. And there is another process much more significant in case of the tissues, when the positron from the atom, from the orthopositronium atom may annihilate with the electron from, which is electron bound to the surrounding atoms. This is called the Pigov process, and this is also shortening the lifetime. So these 2 processes, and this is well known in the material science, are shortening the lifetime. But at the other hand, by measuring the lifetime, we in principle can have an access to the concentration of oxygen and to the size of the free voids. Now the question whether this, how it converts to some diagnostic to the medical indications or the medical. Hello. So I thought there is a question, but so I will continue. So here you see the pressure of oxygen in a tissue as a function of various tissue types for cancer tissues and for healthy tissue. In the healthy tissue, there is always larger. This is on the average. And now that difference can be converted to the differences in the orthopositronium lifetime. When we would consider water, differences would be not large, in the order of a few picoseconds. Therefore, it will be not that trivial to use that for that purposes of hypoxia assessment, but in other organic liquids, this may be even 10, maybe even 20 times higher difference. So how it will be in the body is was not studied by now. So this is one of the good research way to test how in a real body, in an organism, we could how precise we can measure the lifetime and whether that precision will be enough to distinguish between the hypoxic and normoxic condition is the interesting question, I think, and worth to study. So we did studies in the laboratory with the sodium source, because to measure the lifetime, we need to know when positronium was formed. And for that, we need an isotope which is emitting additional photon, like you see here in case of sodium. it converts to neon, and that neon is in excited states and emits a photon. The important thing is that the excitation has to be within a picoseconds, otherwise we would lose the information about the time when the positron was injected into the body. So here you see an example of the spectrum which we observed with the detector. And you see here the Compton edge, because we have only photoelectric effect. Compton edge from the 511 photons, Compton spectrum with the Compton edge from those prompt photons from neons, and the enhancement here due to the lower photons originating from the scatterings in the detector, and also from the decays of orthopositronium. But we can distinguish well and uniquely prompt photon, taking the energy loss. This is an example of the lifetime spectrum with the cylinder measured with the tomography system. So these are accidental coincidences. Here you see the signal from direct and parapositronium, and this is the signal from those orthopositronium produced in that special material in the cylinder with the lifetime of 90 nanoseconds. This is a logarithmic scale. So this was just to show you that it works, that we can, with the plastic scintillators, reconstruct an images. This was that phantom, and we can measure the positronium lifetime with that system. So then we went to trying to make an image and a lifetime simultaneously, and to make it attractive for the medical research, we took the cancer cells operated from the patients, put it in the detector with the sodium source inside. So these positrons were irradiating cancer tissues, it was cardiac myxoma, and healthy tissues simultaneously. So by registering these two gamma photons, we could just make an image like the standard PET of the density distribution of the annihilation. So these are those four sources here. But by measuring the additional gamma, we could determine for each voxel here a lifetime spectrum. And from that lifetime spectrum, the time between the emission of positron and the annihilation, this is the lifetime spectrum, we could extract various parameters. And one of them is the lifetime of orthopositronium atom, which is shown here. So this is now an image, of lifetime of orthopositronium atoms within these tissues here. And interesting was to observe that in those healthy tissue, which in that case were adipose tissue, it was much larger the lifetime than in the cardiac myxoma, which was about 1.9, and in that adipose tissue was about 2.9, so significantly different in that case. And this we measured with the collaborations of the medical doctors under the guidance of Professor Stempin for many patients, and the difference was always significant. So then, and now I am coming slowly and closer to that proton beam monitoring, but before then I will show you how we went to the clinics with the detector. So we could not take this laboratory system. So we made a system which was modular, as you have seen on this animation. This is a photo of that system, but that patient inside is just a superimposed image. The detector allows to measure 3 photon and prompt gamma, 2 photons and prompt gamma. These are the annihilations of or the events of interest. And we can form it in a shape which is useful for a given purposes. So in that case, we make a semi-cylindrical shapes, like you see here, thus to be able to surround with the detector a patient. So we did not need to shift the patient into the detector, but we can just come to the patient and shift the detector on the patient. This is from the laboratory, just a test of the students. So it was a long action. Like in 2019, we started to arrange such studies with the patient. We wanted to do it with scandium, therefore we did it in Warsaw when the scandium isotope can be produced. So here is Professor Królicki, the head of this nuclear department, Professor Bilewicz, who can attach scandium to the ligands, and Professor Choiński and Kilian, who can produce scandium, but by now we did not manage. So we did not manage to get a committee, ethical committee by now, but this is on the way to inject scandium to the patients. So we did the measurements with the gallium. Gallium has advantage that it's also decays via emission of positron to the pin, which then emits prompt photon, but this is only in about 1% cases. In most of the cases, it's just like fluorine decaying to the emitting positron to the ground state. So gallium was good because it has that prompt photon for the lifetime measurement, but it has it only in 1% cases. So we did not expect any high statistics. And here you see it was the first time we went to the hospital, and this is how the installation of the tomography system looks like. The full tomography system with 50 centimeter field of view was just rolled like a 60 kilogram objects to the hospital. Then we were able to install that on a patient bed within an hour. And we were able to take the data just almost immediately after coming to the hospital. And this is how we did it. The ethical committee gave us 10 minutes. So we are allowed to come to the patients with the detector, with the tomography system, install it, take the data, whatever is still decaying from the patients, and go out, such not to bother the patient. So this was not optimum conditions, but this shows you the potential of that system for making tomography in a much easier way than it is so far. And these are our first images, not corrected by now by the scatter in the patients, not corrected for the accidental coincidences, just more or less raw images when you can see all the organs. And this is compared to that Siemens image, which is sharper. But these are images corrected for these many effects. But anyhow, it from the first time with the low activity, low statistics and without corrections, we have shown that it works. But maybe the most exciting was we also took a measurement with the patient with the glioblastoma cancer. The patient was then shifted to our system, just as you see here. So the tomograph was at the end of the Siemens. The patient was shifted here on a bed and the head was here, as you see on that photo. And we took the data with the gallium isotope. We registered double coincidences, triple coincidences, all the possible signals. And from that, when we have three, we could identify prompt photon from the tin and to calculate the lifetime. And the position we knew from the time difference between that two annihilation photons. So here you see a standard images. You see also not only glioblastoma, but also in salivary glands, because the patient was also given PSMA ligand, which has high affinity to the salivary glands as well. But this is just to show you that even with that not optimized prototype, we can make with that plastic detector now images. It is by far not the final sensitivity and the resolution. And we could measure that prompt photon. And here you see an image, which is maybe not that great, but for me and colleagues, it was highly exciting to see that we could see an events from the triple coincidences at the same planes when we see also on the standard PET glioblastoma and salivary glands here. So the main activity was coming from the glioblastoma. And we could calculate the lifetime for glioblastoma cancer in a living patient for the rest of the brain and for the salivary glands. And here you see the results. We see differences. So this is the first that nice point, that in the glioblastoma it was smaller than in salivary glands and even smaller than in the healthy brain. Errors for the orthopositronium are large because the statistic here is very low. And one of the reasons is gallium. Another reason is still our low sensitivity of the detector. But if we calculate the positron lifetime, the average positron lifetimes, then the averages are, the differences are highly significant between these two. And this is just to show you the first trial to show that one can make an images of positronium in a body. And now I will come with that detector to you prepared of how it works, what we started to develop for the proton beam monitoring for the, and here you see again that detector, which is just to show you that this is modular. It's like 24 modules like that, and one can arrange them in various systems. So I think I cannot this community impress with that image, so I will go further. So this is now our detector. We tomograph, but arranged in two blocks, 3 times 4, as you see here, 3 times 4. We just put it, arrange it like that to be able to put it easy on the gantry, on the proton gantry in the proton therapy center. So here you see the part of the group who was taking part in that, and I think I would be nice to mention the colleagues from the hadron therapy who are seenable here, the Antoni Ruciński and Jan Gajewski, and also the colleagues from our group were taking part in that. So here you see how this is a JPET group. We were helping to Dr. Riediger, who was running the beam of protons. The radiation was from here. Our detectors were here, and here was the phantom. Maybe it's better seen here. So here are a few examples. We use phantom. We use this PMMA phantom, which has composition, let's say, close to that what one elemental composition what we have in a body. So we are irradiating the phantom, and as we know, some of the protons are interacting with the nuclei and producing radioactive isotopes. Here is a list of some of those isotopes. Some of them are emitting positrons, and then we can image these positrons. So here you see the possible reactions which leads to the productions of these beta plus isotopes, and some list of them. I will concentrate here on carbon 11, 10, and oxygen 15 and maybe 14. This is what we expect. These are the estimations and calculations. So mostly we expect signal from the carbon, from the oxygen 15 and from carbon 11. So these are the two main which we expect. So this is depending on the time, the composition of various isotopes depending on the time. These are the number of decays per second. In that case, if we would look for the distribution of that activity of positron emitters, it will not look like the distribution of the energy deposition, which is here you see this black peak. This would look rather like that. At the end, there is no enough energy to make the nuclear reactions producing the isotopes. But these two distributions are correlated in space. And from that, by measuring that, one may infer about the beam, the black peak position. But before starting the measurements, we make a lot of simulations. And here you see our two recent articles. The simulations were done, as you may imagine, long time ago, but it took some time to elaborate all this and write two articles. Now they are published. So we studied very many different configurations, as you see here, but at the end we just make the first study with the simplest one, taking the two heads around the irradiated phantom. And here is again simulations. What distributions of activities we expect to reconstruct in case of the single pencil beam, any case of the spread out tactic, as it is more for the realistic case. Here you see reconstructed image of annihilations in that phantom which we irradiated. We used also another phantom which was more complicated, just to test the more realistic conditions. These were like 4 distinct phantoms, water with agar, and this was in the plastic container. So 4 separated cubics, let's say, which were irradiated with different energies and different beam arrangement. Different energies allow us to study different range. Since you are an expert, I cannot hide one thing, that this was our first trials and we failed to detect effectively the data during the irradiation. So here you see when the beam is on, we were registering only a small part of the events. When the beam is off, then we see smoothly the annihilations from positrons in that phantoms. And this is now we work on that, and now we are working on the next generation. So we think we will be able also to take effectively data even though the beam is on. And this is especially possible because of the plastic scintillators, which has a very short signals. So now we will, for the next generation, we will have electronics which will allow also to take the data while phantom is irradiated. So here you see again that what I was just explaining. Maybe some more structure of the beam on, beam off, beam on, beam off, and so on, until the full square is irradiated. And then we did it for various expected ranges, just to be able to compare then whether we can reconstruct that range from our image reconstruction. And here you see, and again, as in the case of these patients, these are not corrected for any effects, just the raw images of annihilation in that materials. One of the things which is, so one see the end of the beam, as we would like to see, the relatively sharp end of the distribution, which is correlated with the Bragg peak. But we see also some enhancement at the beginning, and this enhancement is due to the different material of the plastic, which is mostly carbon, and here is water with agar. And this we could prove, because this is now the projections of that image. So we see the first everything all the time, like half an hour of acquisition. Here we see the acquisition of the later events after 5 minutes, and here we see those which are the first 5 minutes. And in the first 5 minutes, we do not see that enhancement here, because there is no oxygen in that plastic. Plastic is mainly carbon and hydrogen. So we could understand the shape of this non-standard shape of those images, but we can only see quite smooth edges, which we can fit in that case, we feed it with the sigmoid function, but anyhow, whatever that can be, that can reflect that shape at the end. Now we correlate this, let's say the center of that. In our case, we just tried the center of that distributions when there is a change of going through half of the spectrum. And this is the comparison of the differences, because we don't want now to, in that first trial, at least at this stage, we don't, we have no now correlations of the absolute positions of the Bragg peaks. But what we can do, just to verify the method, we can look for the relative differences between different settings. And here you see the relative ranges. We have a lot of combinations from that studies. So we could make it for very many relative settings. Here you see what was set and what we reconstructed. And this is proof for us experimentally that we, even with that simple system, not optimized, we've not optimized, we can make it much more efficient and covering better the range around the patient. But we can, even with that system, we can reconstruct the position of the, if we correlate it someday with the Bragg peak, position of the Bragg, of the edge of the irradiations is better than 1 millimeter. So this is with the precision, which is fraction of the millimeter. And now, and now this is that like now thinking whether we could also make the images of or the studies of lifetime of positronium or positron lifetime. For that, we cannot do with carbon-11, but we can do it with carbon-10, which is having that additional prompt photon, or oxygen-15. So in principle, it is possible, but now it's like opening a new research for us to try to see whether we would be able to. It's also maybe encouraging for some of you who would be interested to see whether one can measure. First step would be the lifetime of positronium and positrons in photons or in a body, and then the next step, probably a long-standing research to correlate it with the hypoxia. And as the last, just few slides I will complete now, I will show you at which stage we are with that total body system. So now we are doing from the point of view of the tomography, at least for us, as a research facility, the last step of making a system which will be like 2.5 meters, such long because we would like to avoid the edge effects, to have a sensitivity along the whole patients with high value and flat sensitivity. This system will be able to measure decays into 3 photons, 2 photons, and prompt, but we also aim to be able to measure the polarization of those gamma quanta. And polarization we can measure by measuring the Compton scattered photons, which is possible with that detector. So this will be a system which we do in order to make dynamic studies of metabolism in a body, and also to make a research on positronium inside the human body, and maybe also that to see what one can learn from polarizations, which is again an open issue. This is how the detector may look if it would be covered with the plastic scintillator, with some plastic cover. We have already a design, technical design, almost ready. And we built the first prototypes, first detection systems, which is a newer generation that I have shown you with the modular PET. And this will be the system where the patients will be not moved, the patients will be lying on a bed, and we will make a CT. Maybe at some stage, after some years, we will maybe even not make a CT if one can make that attenuation map from the PET itself. And the PET will come, and the patients will be able to close and open this. Because from plastics we may make it relatively light. So with that perspective, I would like to finish that talk. Thank you for your attention.
Thank you very much, Pavel. Very interesting. I'm sure we will have questions, but before the questions, we would like to take a Zoom photo. So Angelica, on the ready. Could everybody turn their cameras on, please?
Can you, Power, please stop sharing the screen so I can have all the...
I did.
Thank you.
Yeah, thank you.
That's perfect.
Thank you very much.
So please turn on your videos.
Yes.
In the meantime, get ready.
Okay. I will do that. Just another second. In the meanwhile, think to the questions, please. And I will manage.
Okay, so...
okay, yeah.
Okay, great.
Got it.
Thanks a lot, Angelica. So for
Thank
questions, you can either raise your hand or you could put them in the chat. So please go ahead. Don't be shy. Don't see any raised hands. So I have a question then. Okay, Pavel. So what next?
So next, as I have shown you, at least in the next few years, we will, on the hardware side, we will be occupied with constructing that total body PET system, which will cover the whole body and taking that into the operation. So this optimistically will take maybe 3 years. And then we will be at the more clinical level to make more experiments with humans. Although we are doing it, as you have seen already now, with that prototypes.
Okay.
And we plan in the future, when we have a new updated electronics, we will go once more, at least once, maybe more times, to the hadron therapy centers to make the study with that modular prototype, but with the updated electronics, so we can take data also during the beam on. So this would be like the aim is to develop the system up to the stage that it can make online on beam.
Okay, great. Thank you.
Monitoring.
Yeah.
So this is
so some question on chat, but I have 2 questions for you. How long does a whole body PET take with such a system? And we talk about cheap. How cheap would it be to a conventional whole body PET?
So I can tell you. So this has to be disclaimer, because one number I know very precisely, which is what we are doing. So we got a grant which we got from the ministry to build the total body system, which is including the prototyping and also the paying for the personnel, is $3 million, $3.5 million. And with that, we like to build that 2.5 meter in the prototype phase total body PET. And from what I know, but I has to tell it once more. I don't know, but from what I heard, is that the half total body system, like 1 meter Siemens, costs about €9 million.
Okay, thank you. And timing, does it take a lot longer to do whole body imaging, you think, than
So
crystals?
so this is always the subject. Total body systems give some opportunities, either due to the higher sensitivity, either to measure for shorter time, or to measure with the lower dose. And the numbers which counts here is the which is called in PET sensitivity, what in physics we call efficiency for the gamma registrations. So we expect, this is from the based on the simulations, to have it 20 times for the total body, 20 times higher than the present 20 centimeters PET. But like Explorer, this one in US or Siemens, they have it even much more higher than this factor of 20.
Okay.
Explorer was more than 40.
Okay.
So it's more. But so the sensitivity will be less than with that crystal, but it still will be much, much higher than it is now. So it will allow to make the dynamic image.
Thank you. So there are two questions on chat. One from Tim Greenshaw. Would there be advantages to using silicon photomultipliers, or are they too noisy for your purpose?
Silicon. So the first detector which I have shown, because this was still designed long, like in 2012, and then we got money later, so we proceed with vacuum tube photomultipliers. At those days, they were better in timing than silicon, but this total body as well as this modular, which we now use in the hospital, as I shown you, is from the silicon. The readout is from the silicon photomultipliers. So we already changed to silicon photomultipliers.
Okay, great. So question, yeah, sorry.
So they make it much more easy to handle such a detector system.
Okay.
Robust, yeah.
Okay. Tim, if you want to follow up, go ahead. Sorry.
No, it's just they have obvious advantages in the clinic, like no HV and things like that, so much easier to use. Yeah.
Okay, great.
40 volts instead of 2000.
Yes, that makes the patients much happier.
Yes, absolutely. So Richard, do you want to ask your question yourself, or you want me to read it?
Either way, you can.
No, why don't you go ahead?
Are you planning to do any tests in animal models or indeed humans to in vivo to measure range?
So I have to now admit honestly, we do not have any well crystallized plan by now. So because everything takes time. So our first step towards the proton range verification is to come to the stage that we can take data online on beam with the new electronics, and then and this we hope to do by the next year, let's say. And then if we manage to encourage the colleagues from that hadron therapy center and some like animal models, some preclinical researchers, then it would be a way to go. But so honestly, by now we have not such a collaboration with nobody.
Right. Okay. Thanks.
Anybody? Any other questions, comments, anything before I thank Pavel and let him go? Oh, there is a question. Alejandro, do you want to ask yourself?
Is there any reason when you perform in vivo experiment to expect something different on the washing effect?
So for you mean now for the range monitoring, or?
Yes.
Yeah. So I mean these are certainly effects which will contribute to the smearing of the distributions, but so we did not make any modeling of that. But in general, what at least as much as generally I can tell is that if we would be able to take data on beam, then we can minimize the effect on spread out to do the metabolic and blood kinetics.
Yeah, that was my question. Time effect on the metabolic part. Thank you.
Manjit, you're muted.
I just realized I was muted, sorry. So thank you very much. Very interesting. Looking forward to the next steps, of course. The
Thank you
whole-body PET.
for that opportunity to present.
Not at all.
results.
Our pleasure. And I'm really, it's really great that you actually see from the first steps all the way to the clinical translation happening. But one has to be patient. One needs lots of funding, lots of collaboration, and multidisciplinary teams, because it takes ages to do this, as we know. It's really nice work. Very nice work, though.
Then I can maybe take opportunity to thank you. And I see also that Dennis is connected, because you were you were the two who accepted a talk at these days when it was not so easy to get a talk at any conference with that project.
You see, we are visionary. What can I say? Teasing. Anyway, so thank you again. Really appreciated it. Let me just take this moment to say our next talk is going to be by Professor Hoffman from Oncore Dresden, integration of MRI and proton therapy. So this is a new hot topic, as you know, and that will be on the 18th of April. You will hear more about it, but just put it in your calendars. So thank you again. Have a nice evening, everybody. And thanks, Pavel.
Thank you. Thank you. Bye.
Bye-bye.
Thanks. Bye.